now we're going to do the review for this unit, chapters. You notice we did 4, 5, 6, and 7. We did 7 as well, which was the periodic table, but I don't really have any test questions because it's kind of stuff we've covered already. So your test questions are going to go 4, 5, and 6, okay? One of the first things we did was the chart. I don't know if you can see that, the insoluble and the soluble. And you looked on the chart, and if you looked for oxides, you'd see that they're insoluble. Anything with NH4, you guys, anything with ammonia luciferase is soluble. It doesn't matter what it combines with, it's always soluble, okay? Lithium nitrate, nitrates are soluble. And aluminum phosphates, all phosphates are insoluble except for ammonium. But this one, it's aluminum, so it's insoluble. Okay, so why does that matter? When you have a double replacement reaction, remember, you have to finish a reaction. You have your anions and your cations switching partners, and then you got to look to see if one of the products is insoluble, forms a precipitate. And if both of them are soluble, you got no reaction, okay? So that's why it's important to know how to read that chart. You can tell if a double replacement reaction is actually going to occur, okay? So here is a net ionic equation, okay? You can see right here, we got iron chloride and magnesium. We end up with magnesium chloride and iron. All right. So we're going to break it down. This is because it's combined with something. It's iron plus 3, and there's 6 chlorine, 2 times 3. And then we write in our magnesium plus 2. And then over here, we've got magnesium with chloride. And then this iron is by itself, and iron is going to be, this isn't an ion anymore, okay, because it's not combined with anything. Okay, so if we go back through and we cross off the ones that are the same on both sides, we're going to cross off the chlorine and the magnesium. And I know this looks weird, but we got iron as an ion forming ion as a compound, as an element, I should say. Okay, that's kind of a weird one. We'll do some better ones that you're more used to. Okay, so here we have silver nitrate and magnesium iodine, and we get silver iodine and magnesium nitrate. Now the first thing I'm going to do is make sure this reaction occurs. So I'm going to look on my chart, and if I look at iodides, it says all iodides are soluble except silver. So this forms a precipitate, so I know I got a reaction, okay? That's, if you don't have a reaction, then you get to quit. Okay, so now I'm going to break these down. I'm going to keep this guy together because it doesn't form ions, it forms a precipitate. So silver plus, this should be +1, you guys, sorry. I'll fix that later. This is +1. And then nitrate is -1, okay, and the 2 in front. I don't know why I got the 1 there. Okay, now we got magnesium as +2, that's right, and 2 iodine at -1. I broke all these guys down into their ions, okay? Now over here, I keep this guy together because remember, it forms a precipitate, but this doesn't, so I break it down into its ions, okay? And you got to make sure you put the numbers in there. Now I'm going to cross off my spectators, so I'm going to cross off my nitrate, my magnesium, magnesium nitrate. So I'm going to end up with this silver, and again, that's a +1. I'll fix that. Plus iodide yields 2 silver iodide. Okay, so again, this is the molecular, this is the complete ionic, and this is the net ionic. And you got to make sure you got a reaction happening. Okay, here's another one. We got barium nitrate and calcium acetate. We're going to end up with barium acetate and calcium nitrate. Okay, we're going to look and we're going to see, and it says acetates are all soluble. So this one is soluble, and nitrates are all soluble. So in both cases, these are soluble. So I have no precipitate, no reaction. Okay, so if you get one of these where you got no precipitate, neither of these are insoluble, then you don't do any of this because there's no reaction going on. Okay, that's how you do those. Okay, oxidize and reduction. Remember, there's going to be a change in their combining capacity, in their charge. And remember, oil rig, oxidation is loss. It's a loss of electrons. So if it becomes more positive, it's oxidized. And don't think it's oxygen, because most of the time it's not. Okay, and then oil rig reduction is gain. So they become more negative. They gain electrons, okay? So if you look here, I look for elements by themselves. So I got carbon by itself, okay? So here carbon is 0. Whenever you got an element by itself, it's 0. And then over here it's combined with oxygen. Oxygen's -2. So 2 times -2 is -4. So over here, carbon is +4. So we go from carbon 0 to +4. Okay, so it becomes more positive, it's oxidized. Okay, I gotta look for one more. Okay, I know it's not oxygen, and most of the time it isn't hydrogen, so the only thing left is sulfur. Over here, sulfur, let's see, we got -8 because oxygen's -2 and there's 4 of them. And we have hydrogen at +1 and there's 2 of them, so I got +2 and -8. So sulfur, because the overall charge has to be 0, is +6. Over here, oxygen's -2 and there's 2 of them -4, so sulfur's +4 here. So here it's +6, here it's +4. Okay, it became less positive, so it's reduced. All right, so what you do is you look for an elements that change. Now, the ones that change, you guys, either elements by themselves, like carbon was here, or sulfur, nitrogen, manganese, phosphorus. Those are the guys that change. Don't look at oxygen and hydrogen much, you know, unless they're by themselves on one side and not on the other side. Otherwise, it's the other guys that are involved. It's the nonmetals, okay? Now, here's another one. I got magnesium and HCl, hydrochloric acid. I end up with these two guys, okay? So magnesium here is 0. Over here, it's +2. Hydrogen is combined here at +1, and over here it's 0. Again, when an element's by itself, it's 0. So this one was easy because I had, you know, ones by themselves on each side. So 0 here to +2, it's oxidized. It became more positive. It lost electrons. Here, hydrogen goes from +1 to 0, so it's reduced. It becomes less positive, or it becomes more negative. Okay, on this one, now I don't have any, I have Sb by itself. So I know that's one of them. So Sb goes from 0, and then over here, I have oxygen, which is -2, and there's 3 of them. That's -6. So this side's +6. 6 divided by 2 is 3. So Sb goes from 0 to +3, and then I need one more, okay? And it's not going to be hydrogen, oxygen, so it must be nitrogen. Here, nitrogen is, let's see, oxygen is -2, and there's 3 of them. That's -6. And hydrogen is +1. So if this is -6 and this is +1, this has to be +5 because the 2 of them, again, have to equal 0. So here, nitrogen's +5. Over here, nitrogen, -2, +2. So it goes from 5 to 2. Okay? So again, antimony went from 0 to +3. It became more positive, so it's oxidized. Nitrogen went from +5 down to +2. And again, it's still positive, but it's less positive, so that's why it's reduced. Okay, so when you're doing oxidation reduction, if one is oxidized, one has to be reduced. You can't have one without the other, but you just look at the charges, okay? And again, look for elements by themselves. That always makes it a little bit easier, but if you don't have elements by themselves, you got to look at what they're combined with. And nitrogen and phosphorus, and those guys are real good at switching their oxidation numbers, okay? Here's another one. Okay, we got chlorine by itself over here, so I know that's one of them. Okay, chlorine here is -1. Chlorine over here is 0 because it's by itself. So there's one. Now I got to look for the other one. And again, it's not going to be potassium. I already did chlorine. So it must be manganese. Okay, so here I have 4 oxygen. 4 times -2 is -8. Potassium is 1. So manganese must be +7. +1, +7, that's +8. This is -8. So here manganese is +7. Over here, chlorine's -1 and there's 2 of them, so it's -2, so manganese is +2. So it goes from 7 to 2. Okay, so again, the chlorine here was combined with hydrogen, it was -1. Over here, it's by itself, it's 0. So it went from -1 to 0, it's oxidized. Okay, it's more positive, right? Because 0 is more positive than -1. Manganese goes from +7 to +2. Over here, it was +7, here it was +2. So now it became reduced. It's less positive. That's how you figure them out, okay? All right, here's specific heat. Remember, mass times specific heat times change in temperature equals Q. Q is the amount of heat lost or gained, okay? So if I'm doing this one, I'm going to go 52 grams times specific heat times the change in temperature. Just multiply them all together, okay? And again, I know my unit is joules because here I had grams, here I had that. They cancel out. Got my answer. Okay. If I want to find specific heat now, I'm going to take the amount of heat lost or gained and divide by the mass and the change in temperature. Okay. So what I did here is I took my heat, because I already know that, and I divide it by my mass, and then my change in temperature, 53 minus 12 would be 41. And if you look at here, grams Celsius, you got all the units there. So if you're trying to find specific heat, you do it this way. If you're trying to find heat lost or gain, you just multiply all three numbers. Okay. All right. What do we got here? Okay, we're trying to figure out the amount of heat. Now, remember when it writes it like this, okay, we've got delta H is plus 128. That means the heat's over here. That means it's endothermic. If this was minus 128, it would have been over here. Okay, how many kilojoules of heat are consumed when 15.5 grams of CH3OH decomposes? Okay, so we got the equation. So what I do is I take what I know, 15.5 grams of CH3OH, 1 mole. The 32 is the mass of this. I took 1 carbon, 4 hydrogen, and 1 oxygen and added them together. And that's where I got that. Okay, and I'm sorry there's not labels on here, but then they don't fit on the line. Then I put 1 mole here, because if you look at my equation, there's only 1 up here. Now, if there was a 2 here, I'd put a 2 here. But when there's 1 mole of this substance, this is how much energy. So I put that on top. So it's just 15 times 128.1 divided by 32. And you get 62.05. That's how many kilojoules. Now, if you had 1 mole of this, you would start with 32 grams. And you would get, this is your amount. But since you don't have a full mole, then you've got to adjust. Okay, and again, this is the mass of that. And this number right here depends on what coefficient you got here. In this case, it's just 1. Okay, here's another one. Okay, again, now delta H is negative, so we know this is an exothermic reaction. Okay, so what I'm going to do, it says how much heat is released when we have 89.5 grams of oxygen reacts with an excess of carbon dioxide. Okay, so I start with 89.5, what I know. And now I got to get rid of grams of oxygen, change it to moles. So it's 32 again, just like the last one. But why do I know it's 32? Oxygen 16, and there's 2 of them. That's why it's 32. Okay, and then this is the amount from when you have a regular reaction right there. And again, I don't have a number here, though, so that's why it's 1. If it was carbon monoxide, I would have a 2 here. Whatever the coefficient is that's what you'd put here. And then you just multiply and divide, and that's what you get. This is an exothermic reaction, negative. Okay, and now I have more than 1 mole of oxygen. That's why it's bigger than this number. Okay. This is the chart using your bonds. It would be, if you remember these, you should have that chart somewhere. Okay. So I'm going to write this out. See, I have 4 CH bonds because there's a CH here. See, carbon is bonded with hydrogen in 4 different places, so that's why I have 4. And this number, if you look on your chart for carbon hydrogen, is 413. Then I put 2 here, and oxygen is specifically listed on your chart. It's 495. Oxygen forms a double bond, but it's right in there. And then since there's a 2 here, 2 by that. Here I have carbon dioxide. Okay, carbon dioxide forms a double bond O. All right, so there's 2 of them because it's O2. So that's where the 799. This is a double bond O, and since there's 2 of them, that's why I had to multiply by 2. Okay, there's no 2 here, but there's a carbon oxygen and a carbon oxygen. So that's why there's 2. And then here, I have a hydrogen oxygen. There's 2 in every unit here, right? And since I got a 2 in front, I had to make it 4. So there's 4 hydrogen oxygen bonds. And again, you look that number up. And then you just do the math, fill in the numbers. And you get negative 808 kilojoules. This is an exothermic reaction. Energy is going to be released, which makes perfect sense because this is a combustion reaction. There's always energy released in a combustion reaction. Okay, so again, you have to look at the number of bonds and you have to use the numbers, and then basically you take these and you subtract, you add this together and then subtract them. It's this number minus these numbers to get your answer. And it's another way to figure out if you have an endo or an exothermic reaction. Okay, there's a few more slides. I'm going to quit here so that I don't have to go through them really fast. And so we'll have 2 parts to the review.